What if the next chapter of human civilization wasn't written on Earth at all, but among the stars? Picture a world where floating cities orbit our planet, where families wake up to artificial sunrises, and where children play in parks under domes of steel and glass, all while experiencing gravity just like back home. This isn't science fiction anymore. The race to build artificial gravity habitats is heating up, and it could redefine everything we know about living beyond Earth. For decades, zero gravity has been the Achilles heel of space exploration, causing muscle atrophy, bone loss, and even vision impairment in astronauts. But what if we could take gravity with us, creating environments where humans not only survive but thrive in space? The idea of artificial gravity has tantalized scientists and dreamers since the dawn of the space age. Remember those iconic spinning space stations from classic films? Turns out they weren't just Hollywood fantasy. Today, visionary companies and space agencies are pouring billions into turning that dream into reality. From colossal rotating stations to moon bases with centrifugal force, the technology is closer than you think, and the stakes couldn't be higher. If we crack this challenge, it opens the door to permanent settlements on Mars, asteroid mining colonies, and perhaps even interstellar travel. But how does it actually work? What are the engineering hurdles, and who's leading this audacious charge into the cosmos? This journey isn't just about gears and equations, it's about rewriting the future of humanity. Imagine a time when moving off-world isn't a perilous sacrifice but a realistic choice, where grandparents can video call their grandkids on Earth from a thriving lunar city. The implications are staggering. New economies, cultures, and even forms of human adaptation could emerge. But to get there, we'll need breakthroughs in material science, propulsion, and biomechanics, all while racing against time as Earth's resources strain under growing demands. So buckle up. Over the next few minutes, we'll unravel the science behind artificial gravity, meet the pioneers turning theory into reality, and explore how this single innovation could unlock the solar system for generations to come. The countdown to living among the stars starts now. The key to unlocking artificial gravity lies in one simple principle: rotation. Picture a giant spinning wheel in space, where the outward push created by centrifugal force mimics the pull of gravity here on Earth. This isn't just theoretical. It's the same physics you experience on a merry-go-round, where faster spins make you feel heavier. But scaling this up for human habitats introduces fascinating challenges. Too slow and the effect is barely noticeable. Too fast and astronauts might struggle with dizziness or nausea. Our inner ears weren't designed for constant rotation. That's why scientists are meticulously calculating the perfect balance between size and speed. A habitat with a diameter of several hundred meters, spinning at just the right rate, could create a comfortable one-Earth gravity environment without disorienting its inhabitants. Beyond spinning structures, researchers are experimenting with other innovative approaches. Linear acceleration, think of a spacecraft constantly thrusting forward to simulate gravity, could work for interplanetary travel, though it would require staggering amounts of fuel. Then there's the wild card, magnetic fields. While still in early stages, some propose using powerful magnets to manipulate the body's molecules, effectively creating a gravity-like force. But for now, rotation remains the most practical solution, thanks to designs like the O'Neill cylinder, a visionary concept from the 1970s that's inspiring today's engineers. These massive rotating tubes could house entire cities with landscapes, rivers, and even weather systems under their curved roofs. But here's the catch: building these structures isn't just about physics. It's about human biology. Without gravity, our muscles weaken, our bones lose density, and our fluids shift unnaturally, problems that could be solved by artificial gravity, but only if we get the details right. Too much rotation at the wrong speed could make simple tasks like walking feel like navigating a funhouse. That's why prototypes on Earth, like short-radius centrifuges, are testing how different rotation rates affect volunteers. Every discovery brings us closer to habitats where humans can live, work, and raise families without sacrificing their health. The science is complex, but the goal is simple: to make space feel like home. The dream of artificial gravity began long before rockets pierced the atmosphere. Back in the early 1900s, Russian scientist Konstantin Tsiolkovsky, often called the father of astronautics, first sketched rotating space stations that would generate gravity through centrifugal force. His visionary blueprints, drawn with nothing but pencil and imagination, laid the foundation for everything that followed. Fast forward to the 1970s, when physicist Gerard O'Neill took the concept even further. His detailed designs for massive cylindrical habitats, complete with farmland and lakes under transparent domes, weren't just technical proposals. They were invitations to reimagine humanity's place in the cosmos. NASA didn't just theorize, they put these ideas to the test. During the Gemini missions of the 1960s, astronauts spun their capsules in space to study how rotation affected their bodies and perceptions. Some reported dizziness, others nausea, proof that artificial gravity wasn't as simple as spinning a spacecraft. But these early experiments were crucial. They revealed the delicate balance between rotation speed and human comfort, lessons that still guide engineers today. Now, private companies are pushing boundaries even further. SpaceX's Starship prototypes and Blue Origin's orbital ambitions aren't just about reaching space, they're about staying there. These modern pioneers are designing habitats with rotation in mind, learning from decades of research while embracing cutting-edge materials and construction techniques. The shift from government-led programs to private innovation has injected fresh energy into the field, accelerating progress in ways Tsiolkovsky and O'Neill could only dream of. Yet for all these advances, the biggest breakthroughs may still lie ahead. Recent studies on the International Space Station are testing how partial gravity affects bone density and muscle retention. Meanwhile, startups are prototyping compact centrifuges that could fit inside future moon bases or Mars habitats. Every experiment, whether in orbit or on Earth, brings us closer to answering one pivotal question: how do we make space feel less like an outpost and more like home? The journey from Tsiolkovsky's sketches to tomorrow's orbiting cities is far from over. But with each milestone, we're rewriting what's possible. Living without gravity isn't just uncomfortable, it's a silent, relentless assault on the human body. Take astronaut Scott Kelly's year aboard the International Space Station. Despite rigorous daily workouts, he returned to Earth 2 inches taller, with weakened bones, atrophied muscles, and eyesight that had permanently deteriorated. These aren't isolated cases. Nearly every astronaut who spends extended time in microgravity faces similar challenges. Bones lose density at a rate of 1 to 2% per month, equivalent to decades of osteoporosis crammed into a single mission. Muscles, no longer fighting gravity's pull, waste away even with constant exercise. And perhaps most alarmingly, fluids that normally pool downward in Earth's gravity drift upward in space, pressing on optic nerves and blurring vision, sometimes irreversibly. The consequences go beyond physical health. Without gravity, the body's circadian rhythms, the internal clock that regulates sleep, become erratic. Immune systems weaken. Even simple tasks like swallowing become trickier when liquids float away instead of flowing downward. These aren't mere inconveniences, they're fundamental barriers to humanity's future as a spacefaring species. Consider Mars. A round-trip mission could last 3 years. Without artificial gravity, astronauts might arrive too physically compromised to explore, let alone establish a colony. Current countermeasures, like the ISS's treadmills and resistance machines, are stopgaps at best. Astronauts dedicate 2.5 hours daily to exercise just to slow the damaged precious time that could be spent on research or maintenance. And while medications can mitigate bone loss, they bring side effects of their own. The harsh truth: zero gravity is a hostile environment for human biology, evolved over millions of years under Earth's constant pull. That's why artificial gravity isn't just a luxury, it's a necessity. Without it, long-term space habitation becomes a game of diminishing returns. Children born in microgravity might develop skeletal systems too fragile for Earth's gravity, trapping future generations off-world. Mining asteroids or building lunar bases would require constant crew rotations, inflating costs and risks. The solution isn't to adapt humans to space, but to adapt space to humans. By recreating gravity, we're not just preserving health, we're preserving choice. The ability to return home, to live sustainably among the stars, and ultimately, to ensure that life beyond Earth isn't a sentence but a future. NASA didn't just pave the way to space, it redefined how we think about living there. Decades before private companies entered the race, NASA scientists were spinning astronauts in centrifuges, strapping volunteers to rotating beds for weeks, and even testing short-radius artificial gravity setups in aircraft. These weren't stunts, they were critical steps to answering a fundamental question: can humans thrive in space without Earth's gravity? The results were eye-opening. Early tests showed that even 30 minutes of daily rotation could significantly reduce muscle loss and fluid shifts, offering a glimpse of a future where artificial gravity isn't optional, it's essential. Now, NASA Artemis program is taking that research to the next level. The Lunar Gateway, a space station orbiting the Moon, isn't just a waypoint for astronauts, it's a laboratory for the technologies that will make artificial gravity a reality. Scientists plan to test rotating habitat modules there, perfecting the balance between comfort and functionality. The Moon's weaker gravity, just 1/6 of Earth's, makes it an ideal testing ground. If we can engineer habitats that compensate for low gravity there, the same principles could apply to Mars or deep space missions. But NASA isn't working alone. The European Space Agency's Moon Village concept envisions a collaborative lunar outpost where international partners share knowledge and risks. Japan's space agency has experimented with artificial gravity in space stations, while Russia's decades of microgravity research inform today's designs. This global effort isn't just about sharing costs, it's about pooling expertise to solve one of humanity's toughest engineering challenges. Yet government agencies alone can't sustain this momentum. Budget constraints and shifting political priorities have often slowed progress, which is why private companies are now driving the most audacious advances. SpaceX's Starship, designed to carry massive payloads, could one day transport the components of rotating habitats. Blue Origin's Orbital Reef project envisions a mixed-use space station where artificial gravity modules could host everything from labs to tourist lounges. The shift from taxpayer-funded missions to private investment has injected urgency into the field, turning what once seemed like distant dreams into near-term possibilities. The lesson here is clear: artificial gravity isn't just a scientific challenge, it's a collaborative one. Whether it's NASA, a rigorous research, international partnerships, or private sector innovation, each piece accelerates the day when humans can live beyond Earth without sacrificing their health. And as these efforts converge, one thing becomes certain: the future of space habitation won't depend on defying gravity, but on recreating it. Private companies aren't just joining the race for artificial gravity, they're rewriting the rulebook. Take SpaceX's Starship, a game-changing spacecraft designed to carry unprecedented payloads into orbit. While its primary mission is Mars colonization, the real innovation lies in what comes next. Picture this: once Starship reaches orbit, it could deploy massive rotating habitat modules, their curved walls spinning gracefully to create Earth-like gravity for future Martian settlers. Elon Musk has hinted at designs where entire sections of the ship rotate during the months-long journey, ensuring astronauts arrive on Mars strong enough to step onto the surface without months of rehabilitation. Then there's Blue Origin, Jeff Bezos's brainchild, which is tackling the challenge from a different angle. Their orbital reef project isn't just a space station, it's a blueprint for a bustling off-world economy. Envisioned as a mixed-use business park in low Earth orbit, it could feature gravity-enabled sections where researchers, manufacturers, and even tourists live and work comfortably. The key innovation: modular spinning rings that attach to the central hub, allowing different gravity levels for different needs. A lab might use Mars-level gravity for experiments, while a residential pod mimics Earth's pull for long-term cruise. This flexibility could make Orbital Reef the first truly customizable space habitat. Not to be outdone, Sierra Space is pushing boundaries with its life habitat, a 3-story, inflatable module that could one day incorporate rotation. What makes Life revolutionary is its compact launch size, expanding like a balloon in orbit to triple its volume. Now imagine clusters of these modules linked together, spinning around a central axis like beads on a string. It's a design that balances practicality with scalability, perfect for everything from lunar bases to deep spaceway stations. What sets these companies apart isn't just their technology, it's their speed. Unlike traditional space agencies bogged down by bureaucracy, private firms can pivot quickly. When SpaceX's early prototypes exploded, they iterated within weeks, not years. Blue Origin's team reportedly cut habitat design timelines in half by using advanced simulation software. Sierra Space's engineers collaborate directly with commercial partners, ensuring their habitats meet real-world needs from day one. This agility is accelerating progress in ways government programs alone never could. But perhaps the most fascinating aspect of this private sector race: the unintended collaborations. SpaceX's heavy lift rockets could launch Blue Origin's habitat modules. Sierra Space's inflatable tech might integrate with Orbital Reef's docking system. Even as these companies compete, their innovations are creating a new ecosystem where each breakthrough lifts the entire industry. The result: a future where artificial gravity isn't just possible, it's inevitable. The Stanford Torus isn't just a space station, it's a blueprint for an entire orbiting city. Picture a massive ring, over a mile in diameter, rotating smoothly to create Earth-like gravity along its inner surface. Sunlight pours through mirrors, bouncing off reflective panels to simulate dawn and dusk, while parks, homes, and workplaces line the curved landscape. Designed by NASA in the 1970s, this donut-shaped marvel remains one of the most detailed visions of artificial gravity ever conceived. Its genius lies in stability. The circular shape evenly distributes forces, eliminating the wobble that plagues smaller spinning structures, but building something so colossal in space. That's where modern engineering steps in. Private firms now propose constructing the torus in sections, launched piece by piece and assembled by robots in orbit, a cosmic jigsaw puzzle with life-altering stakes. Then there's Kalpana 1, a sleek, cylinder-shaped habitat that trades the torus's sprawling ring for a more compact design. Named after astronaut Kalpana Chawla, this concept prioritizes efficiency without sacrificing comfort. Its shorter radius means faster rotation to achieve the same gravity, but clever engineering minimizes disorientation. The interior feels surprisingly open, with tiered terraces creating the illusion of a hillside town under a curved sky. What sets Kalpana apart is its focus on modularity. Entire neighborhoods could be added or removed like building blocks, allowing the station to evolve alongside its residents' needs. It's a vision of adaptability, proving that artificial gravity habitats don't have to be static monuments. They can grow and change just like Earth-bound cities. But perhaps the most tantalizing design isn't from NASA or academia. It's from a company called the Gateway Foundation. Their Von Braun station, named after rocketry pioneer Wernher von Braun, could become the first commercial space hotel with artificial gravity. Imagine a spinning wheel in low Earth orbit, where wealthy tourists sip drinks in lounges that hover above the planet's curvature, their feet firmly planted thanks to centrifugal force. The Von Braun station's innovation isn't just its luxury amenities. It's the proof that artificial gravity can be profitable. By targeting space tourism first, the Gateway Foundation aims to fund larger, more ambitious habitats down the line. It's a clever strategy. Use the allure of weightless vacations to bankroll humanity's permanent expansion into space. Yet these designs share a common challenge: the tyranny of physics. Smaller stations must spin faster to generate adequate gravity, but rapid rotation can turn walkways into vertigo-inducing obstacle courses. That's why engineers are exploring tethered spacecraft, where two modules linked by a long cable spin around each other like Olympic hammer throwers. This approach eliminates the need for massive structures, making early prototypes far cheaper to launch. Recent tests by NASA and private startups have shown promise, with tethered systems achieving steady rotation in microgravity. The trade-off: living in a habitat that's essentially half a spaceship, with critical systems split between two distant modules. It's a reminder that every design, no matter how elegant, forces tough compromises between comfort, cost, and feasibility. What ties these concepts together isn't just their spinning structures, but their shared ambition to make space feel ordinary. The true measure of success won't be technological prowess alone, but whether a child born in one of these habitats could stroll onto Earth without stumbling, or gaze up at their orbital hometown from our planet's surface with a sense of belonging. That's the quiet revolution hidden in these blueprints, not just surviving beyond Earth, but thriving there so seamlessly that the line between here and there blurs into irrelevance. Building a spinning habitat in space is like trying to assemble a skyscraper while riding a merry-go-round blindfolded. The sheer scale of these structures presents staggering engineering puzzles. Take materials, for instance. Earth-bound buildings rely on gravity and solid foundations, but in orbit, every component must endure relentless centrifugal forces trying to tear the structure apart. Traditional steel would buckle under the strain, which is why researchers are turning to ultra-lightweight alloys and carbon fiber composites, materials strong enough to handle the stress yet light enough to make launching them economically feasible. Even then, there's the question of assembly. Imagine trying to bolt together a rotating megastructure while wearing bulky gloves in zero gravity. That's why companies like Made in Space are developing orbital 3D printers that could manufacture beams and connectors on site, using raw materials harvested from asteroids or the moon. Then there's the balancing act, literally. A habitat spinning at several revolutions per minute is incredibly sensitive to weight distribution. A single misplaced module or unevenly stored cargo could throw the entire structure off kilter, creating dangerous vibrations. On Earth, architects compensate for imbalances with counterweights and reinforced foundations. In space, engineers are designing smart gyroscopes and automated systems that detect wobbles in real time, adjusting rotation speeds or redistributing mass to maintain stability. Some concepts even propose liquid-filled rings that slosh to counteract imbalances like a self-correcting washing machine in orbit. But perhaps the most ingenious solutions lie in rethinking construction itself. Inflatable modules like those tested by Bigelow Aerospace could drastically reduce launch costs by packing down to a fraction of their expanded size. Picture a massive habitat that unfurls like a balloon once in orbit, its rigidizing materials hardening under sunlight or chemical reactions. Others propose modular designs where smaller spinning units dock together like Lego bricks, gradually scaling up as more pieces arrive. This approach not only simplifies logistics but also allows habitats to grow organically, adapting to changing needs without requiring a single, risky mega construction project. The challenges don't end once the habitat is spinning. Maintenance becomes a high-stakes ballet. Replacing a faulty component on a rotating structure means accounting for Coriolis forces that could send a drifting astronaut spiraling unpredictably. Robotics will likely handle most exterior repairs, but even they'll need specialized programming to navigate the complex physics of a spinning environment. Meanwhile, radiation shielding, already a hurdle for static space stations, becomes even trickier when the entire structure is in motion, requiring innovative materials or magnetic fields that rotate in sync with the habitat. What makes these obstacles worth tackling is the alternative, a future where humans remain forever tethered to Earth's gravity, our biology limiting us to brief, debilitating stints in space. Every solved equation, every tested prototype, brings us closer to habitats where children can grow up strong, where explorers can venture farther, and where humanity's reach finally matches its imagination. The spinning structures of tomorrow aren't just feats of engineering, they're the playgrounds, workshops, and hometowns of the first true spacefaring generation. Imagine waking up in a windowless room where the walls curve upward into a false sky, where down is dictated by spinning metal, and where stepping outside means certain death. The psychological toll of living in artificial gravity habitats might prove even trickier to solve than the engineering. Astronauts on the International Space Station already report a phenomenon called the overview effect, a profound shift in perspective from seeing Earth as a fragile blue marble against the black void. But what happens when that view is replaced by manufactured landscapes under rotating ceilings? Claustrophobia isn't just discomfort in these environments. It could become a full-blown crisis. Studies from Antarctic research stations and nuclear submarines reveal how even sturdy minds crack under prolonged confinement. Add the constant hum of machinery, the absence of natural sunlight cycles, and the knowledge that rescue is days or weeks away, and you've created a pressure cooker for mental health. Yet the challenges go deeper than individual psychology. Social dynamics in a closed ecosystem could make or break off-world colonies. Picture 1,000 people living in a spinning cylinder where every resource, from oxygen to coffee, is meticulously rationed. Petty arguments over noise or shared facilities might escalate when there's no escape. Historical examples like the Biosphere 2 experiment show how quickly group cohesion can unravel. Within months, crews split into factions, and scientific collaboration gave way to interpersonal strife. Now imagine that tension playing out in a habitat where a single act of sabotage could doom everyone. designers are tackling these risks with surprising creativity. Architects draft habitats with vertical villages, stacked neighborhoods that encourage movement and social mixing, counteracting the isolation of cramped quarters. Virtual windows could display real-time Earth vistas or dynamic alien landscapes, easing the sensory deprivation of metal walls. Some proposals even include gravity lounges, where slightly slower rotation rates create zones for relaxation, mimicking the weightlessness astronauts describe as euphoric after months in rigid artificial gravity. But perhaps the most radical shift will be cultural. Isolated communities develop unique dialects, rituals, and values within generations. Now accelerate that process in a habitat where children grow up knowing only artificial sunsets and recycled air. Their concept of normal might involve polyphasic sleep schedules adapted to artificial light cycles, or sports played in curved arenas where Coriolis forces bend trajectories. Over time, these communities could diverge from Earth's cultures as dramatically as ancient seafaring societies diverged from their landlocked origins. The ultimate test won't be whether we can build spinning structures, but whether we can design them to nurture human resilience, a habitat that handles physics flawlessly but grinds down its inhabitant spirits is a ticking time bomb. That's why psychologists work alongside engineers today, ensuring tomorrow's space cities aren't just technologically dazzling, but livable in the deepest sense. Because the future of space colonization doesn't hinge on steel and algorithms alone. It depends on creating places where people don't just survive, but remember how to laugh, bond, and dream under an artificial sky. Funding the future of space habitats isn't just a question of engineering, it's a trillion-dollar puzzle with no easy answers. Consider the International Space Station. Its construction and maintenance cost over $150 billion, funded by 15 nations over 3 decades. Now imagine scaling that to artificial gravity habitats, where spinning megastructures require even more advanced materials and complex assembly. The price tag could dwarf entire national space budgets, forcing governments and private players into uncharted economic territory. But here's the twist: the very expense that makes these projects daunting might also unlock their funding. Space is no longer the sole domain of superpowers. It's becoming a marketplace where ambition intersects with opportunity. Governments will likely shoulder the initial risks, just as they did with the ISS. NASA's collaboration with private partners on the Lunar Gateway sets a precedent. Public funding jumpstarts the infrastructure, then commercial entities step in to monetize it. The European Space Agency is already exploring public-private models for its Moon Village concept, where shared costs could lead to shared revenue from lunar mining or research. But artificial gravity habitats add a new layer of financial complexity. Unlike static stations, their spinning mechanisms require constant energy and maintenance, driving operational costs higher. That's where creative financing kicks in. Tax incentives for companies investing in space manufacturing, or even sovereign wealth funds targeting off-world real estate, could bridge the gap between taxpayer-funded science and profitable enterprise. Private investors aren't just waiting for governments to lead. Axiom Space's plan to attach luxury modules to the ISS hints at a future where billionaires pay millions for orbital vacations, and those funds could subsidize artificial gravity research. Imagine a high-end resort spinning gracefully above Earth, where wealthy tourists bankroll the technology that later enables affordable worker housing on Mars. It's a modern twist on historical exploration. 18th-century trade routes funded by spice and silk now replaced by zero-gravity spas and panoramic space lounges. Companies like SpaceX and Blue Origin are betting big on this crossover, designing reusable rockets to slash launch costs and make orbital construction economically plausible. Yet the most sustainable revenue streams might come from unexpected sectors. Pharmaceutical companies are clamoring for microgravity labs to develop purer crystals for life-saving drugs. Artificial gravity habitats could offer the best of both worlds, controlled environments for research without the health drawbacks of zero gravity. Semiconductor firms, too, are eyeing orbit for manufacturing next-gen chips in dust-free vacuum conditions. Add asteroid mining ventures needing rotating bases to process raw materials, and suddenly these habitats become industrial hubs, not just scientific outposts. The ultimate key: diversification. No single funding source can sustain permanent space habitats, but a mix of tourism, research leases, manufacturing, and even orbital advertising could create a robust off-world economy. The challenge isn't just finding the money, it's building an ecosystem where artificial gravity pays for itself, turning humanity's cosmic ambitions into a viable business model. The race isn't only to construct these habitats, but to prove they can thrive without Earth's endless subsidies. Space tourism might seem like a playground for billionaires, but it could actually be the catalyst that brings artificial gravity to the masses. Picture a luxury hotel orbiting Earth where guests sip champagne in rotating lounges, their glasses staying perfectly level as the habitat spins beneath them. This isn't just fantasy. Companies like Orbital Assembly are already designing these getaways, with plans for their Pioneer station to host upscale travelers by the late 2030s. The twist: these high-paying tourists could bankroll the very technology that makes long-term space living feasible for everyone else. The economics are surprisingly straightforward. Building a single module with artificial gravity costs billions, but wealthy travelers are willing to pay millions per stay for the novelty of floating in comfort. That revenue could then subsidize the construction of additional modules, ones dedicated to research, manufacturing, or even affordable housing for off-world workers. It's a modern twist on how historic railroads funded expansion. First-class passengers covered the costs so freight and economy services could follow. Orbital Assembly's approach mirrors this, with their initial luxury suites paving the way for later scientific and residential additions. But the real innovation lies in how these early habitats could refine the tech. Tourist feedback will be invaluable. Do guests experience motion sickness at certain rotation speeds? How does artificial gravity affect sleep quality compared to zero-gravity pods? Even seemingly trivial details like shower drainage or elevator mechanics in a spinning environment will provide data that textbooks can't predict. Every champagne-fueled vacation could secretly double as a live trial, ironing out kinks before families or factory workers move in permanently. The luxury market's influence doesn't stop at funding. High-end tourism demands aesthetics, pushing engineers to design habitats that feel less like spacecraft and more like five-star resorts. Think panoramic windows framing Earth's curvature, or hydroponic gardens that double as botanical art installations. These touches might seem frivolous, but they are psychologically vital. If future space residents are to thrive, their environments can't just function, they must inspire. The same design principles that make a hotel feel opulent could later ease the isolation of Martian colonists or asteroid miners. Yet there's a fascinating tension at play. While tourism accelerates development, it also risks creating a two-tier system where only the wealthy experience space in comfort. That's why pioneers like the Gateway Foundation emphasize scalability. Their Von Braun station starts as a luxury destination, but its modular design allows for gradual expansion into a multi-use community. The goal isn't just to build hotels, it's to prove artificial gravity works well enough that insurers, governments, and corporations will invest in broader applications. The lesson from Earth's history is clear. Pleasure often paves the way for progress. Cruise ships led to safer ocean liners. Private jets improved commercial aviation. Now, space tourism could do the same for artificial gravity, turning what was once a scientific hurdle into a service people are eager to pay for. The result: a future where the technology that starts with orbiting casinos and honeymoon suites ends up enabling hospitals, schools, and entire cities among the stars. Mars' rusty surface may look like the perfect backdrop for humanity's next chapter, but its gravity hides a silent threat. At just 38% of Earth's pull, the red planet's gentle tug might seem manageable until you consider what happens to human bodies over time. Astronauts on the ISS floating in microgravity lose bone density at an alarming rate. Now imagine settlers on Mars, where gravity is stronger than orbit but still too weak to prevent muscle wasting and fluid redistribution. Children born there could develop skeletons too fragile to ever visit Earth, trapping generations in a gravitational limbo. That's where artificial gravity transforms from sci-fi trope to survival strategy. Rotating habitats on Mars wouldn't replace the planet's natural gravity. They'd augment it. Picture cylindrical living quarters spinning slowly within dome-covered cities, adding just enough centrifugal force to bring the total effect close to Earth normal. Elon Musk's vision for a million-person Martian metropolis suddenly makes more sense when you realize these spinning structures could be woven into the architecture. Residential districts might feature concentric rings rotating at different speeds, offering settlers the choice between Mars' native gravity for short stays and Earth-like conditions for raising families. The key is modularity. Compact centrifuges for sleeping pods where bone regeneration happens during rest, while workplaces embrace Mars' natural gravity to simplify construction. The biomechanics behind this approach are fascinating. Studies aboard the ISS show that even brief daily exposure to artificial gravity, just 30 minutes in a centrifuge, can significantly reduce muscle loss. On Mars, partial gravity workouts combined with rotating habitats could create a best of both worlds scenario. Farmers might tend crops in Mars' natural gravity during the day, then retire to spinning residential modules at night, giving their bodies the full gravitational dose needed to stay Earth-ready. This hybrid model solves another critical problem: energy use. Spinning entire cities would require enormous power, but targeted rotation in key areas keeps energy demands manageable. What makes Mars unique is the opportunity to blend technologies. Lunar bases will likely rely entirely on artificial gravity due to the Moon's feeble 1/6 Earth gravity. But Mars' middle ground gravity opens doors for innovation. Researchers speculate that over generations, Martians might adapt to their planet's pull through gene therapy or biomechanical enhancements. Yet until that future arrives, artificial gravity remains the bridge keeping settlers healthy and their options open. The ultimate goal isn't just survival, but creating a society where moving between worlds doesn't come with an irreversible physical cost. The implications ripple far beyond health. Rotating habitats could determine Martian architecture's very shape. Unlike Earth, where buildings soar upward, Mars' low gravity might favor sprawling complexes unless artificial gravity allows for towering vertical farms and apartment blocks. Cultural norms could emerge around gravity zoning, with different districts specializing in varying gravity levels for sports, manufacturing, or elderly care. Even timekeeping might adapt, as settlers synchronize schedules with habitat rotation cycles rather than Martian sols. Perhaps most crucially, these designs ensure Mars becomes more than a scientific outpost, it becomes a true second home. Without artificial gravity's protective effects, Martian settlers risk becoming a separate branch of humanity, biologically cut off from their earthly roots. But with spinning habitats carefully calibrated to blend Martian and Earth-like conditions, we're not just building shelters, we're preserving the freedom to remain one interplanetary species. The cities of Mars may very well hum with the quiet revolution of rotating rings, each turn a promise that home isn't just where you came from, but where you choose to thrive. The Moon isn't just a destination, it's the ultimate workshop for perfecting artificial gravity. With gravity 1/6 of Earth's, lunar bases offer a unique middle ground between 0G and full gravity, letting engineers test habitats at scales impossible in Earth's thick atmosphere or the void of deep space. Picture NASA's planned Artemis base camp, nestled near the Moon's south pole. Its modules could include a rotating living quarter where astronauts spend months studying how partial gravity affects everything from bone density to crop growth. The beauty of lunar testing lies in proximity. If a bearing overheats or a gyroscope fails, help is only a 3-day flight away, unlike Mars where malfunctions could spell disaster with no quick fixes. This iterative approach is already taking shape. Lockheed Martin's designs for lunar habitats include compact centrifuges, no larger than a small bedroom, where crew members can retreat for a few hours of Earth-like gravity. These gravity gyms could double as laboratories, measuring how much artificial exposure is needed to counteract lunar gravity's weakening effects. Early simulations suggest even short daily sessions might maintain muscle mass better than hours of resistance exercises in low gravity. But the real breakthrough will come from combining these prototypes with the Moon's natural environment. Imagine a greenhouse where plants grow in lunar soil under alternating gravity conditions, some trays spinning to mimic Earth, others stationary to test Mars-like levels. The data harvested could reveal how gravity shapes everything from root structures to nutrient absorption, critical knowledge for future Martian farms. The Moon's weak gravity also simplifies construction in ways Earth orbit can't match. Launching massive rotating structures from Earth requires overcoming our planet's brutal gravity well, but lunar-made components could be assembled with far less energy. Robots might fabricate habitat frames from melted regolith, spinning them up gradually to test structural integrity under increasing forces. Japan's space agency has already proposed using cable-driven systems to tether modules together, creating temporary artificial gravity zones without permanent infrastructure. These low-cost experiments would be prohibitively risky in deep space but become feasible on the Moon's forgiving surface. What makes these tests so valuable isn't just the engineering data, it's the human factor. Astronauts living for months in rotating lunar modules will reveal quirks no simulation can predict. Does walking between spinning and static sections trigger motion sickness? How do shared spaces function when some crew members experience slightly different gravity? Even mundane tasks like showering or cooking need re-evaluation when water behaves differently under partial spin gravity. Each answered question smooths the path for future habitats near Mars or aboard asteroid mining stations. The lessons learned won't just apply to space. Lunar gravity research could revolutionize rehabilitation medicine back on Earth, informing new therapies for patients with muscle-wasting conditions or balance disorders. Spinning beds that alternate gravity levels might help coma patients retain bone density, while compact centrifuges could become standard in nursing homes. The Moon's role as a testbed extends beyond rockets and habitats. It's forging tools that will improve life both on Earth and among the stars. By the time Artemis astronauts return home, their most enduring legacy might not be footprints in the lunar dust, but the spinning prototypes they leave behind, silent laboratories gathering data for the day when artificial gravity transforms from experimental technology to the foundation of off-world living. Every rotation brings us closer to habitats where humans don't merely endure space, but flourish in it. The same spinning habitats designed for spacefarers might hold the key to unlocking medical miracles here on Earth. For decades, scientists have studied how zero gravity ravages the human body, but artificial gravity research flips that script, revealing how controlled rotation could heal. Take osteoporosis, a condition that weakens bones for millions worldwide. On the International Space Station, astronauts lose bone mass 10 times faster than elderly patients on Earth, providing researchers with an accelerated model of aging. Now imagine labs inside rotating space habitats, where scientists can dial gravity up or down like a thermostat, testing exactly what level of force triggers bone regeneration. Early experiments show promise. Mice exposed to intermittent artificial gravity maintain near normal bone density even in orbit. Translate those findings to Earth, and we could see compact centrifuges revolutionizing nursing homes, elderly patients regaining strength through brief daily spins instead of painful fractures. But bones are just the beginning. Artificial gravity research could rewrite our understanding of cardiovascular health. In microgravity, astronauts' hearts shrink and arteries stiffen, mimicking conditions seen in sedentary seniors. Yet aboard spinning habitats, these changes slow dramatically. Scientists now suspect that the gentle tug of artificial gravity might stimulate blood flow in ways that counteract aging. Picture specialized clinics where patients with heart conditions undergo therapy in rotating chambers, their circulation boosted by precisely calibrated centrifugal forces. The implications extend beyond treatment. These controlled environments could become petri dishes for studying diseases. Cancer cells behave differently in varying gravity levels, and rotating labs might reveal why some tumors metastasize while others remain dormant. The most groundbreaking applications could emerge from neurology. On Earth, patients with balance disorders like Meniere's disease suffer vertigo when their inner ear fluids malfunction. But in artificial gravity habitats, researchers can manipulate these fluid dynamics with precision, potentially developing therapies that recalibrate the body's equilibrium systems. Similarly, children with cerebral palsy might benefit from spinning therapy pods that strengthen muscles without joint stress, while stroke survivors could regain mobility in gravity-assisted rehab centers. What makes these possibilities so transformative is their scalability. Unlike billion-dollar space stations, many medical centrifuges could operate in ordinary hospitals. Companies are already prototyping compact human-sized rotors that fit in clinical exam rooms, some no larger than an MRI machine. The technology trickling down from orbital habitats might soon become as commonplace as X-ray machines, turning science fiction into standard care. Perhaps the ultimate irony, the same force that once threatened astronauts' health in space could become humanity's newest medical ally on Earth. As spinning habitats evolve above us, their greatest legacy might not be interplanetary cities, but the lives saved right here through revolutions both literal and medical. Powering a spinning space habitat is like fueling a city that never sleeps while simultaneously keeping it balanced on a cosmic tightrope. Every rotation requires energy, not just to start the motion, but to maintain it against friction and external forces. Solar panels might seem like the obvious solution, but their efficiency plummets when habitats pass through Earth's shadow or venture farther from the sun. That's why engineers are exploring hybrid systems, vast arrays of panels paired with cutting-edge batteries for eclipses, or even nuclear reactors for deep space stations where sunlight is scarce. NASA Kilopower project has already tested compact fission reactors that could provide steady electricity for decades, perfect for habitats near Mars or the asteroid belt. The challenge: making these systems fail-safe, because a reactor malfunction in a spinning habitat isn't just a blackout, it's a potential death spiral. Yet energy isn't just about quantity, it's about quality of design. Traditional space stations radiate excess heat into the void, but rotating habitats must carefully manage thermal waste to avoid destabilizing their motion. Some concepts propose using this heat to warm agricultural zones or melt ice deposits on lunar bases, turning a byproduct into a resource. Others envision superconducting bearings that reduce friction to near zero, slashing energy demands. The most radical ideas skip wires altogether. Lasers or microwaves could beam power from Earth or orbital solar farms, though this introduces precision challenges. A misaligned energy beam might scorch habitat surfaces or miss entirely as the structure spins. Sustainability extends beyond power sources. Every gram of material in a habitat, from steel beams to oxygen recyclers, must be sourced responsibly. Mining the moon or asteroids for raw materials could prevent ecological damage on Earth, but it risks contaminating pristine celestial environments. Water ice harvested from lunar craters might fuel habitats and shield against radiation, but over-extraction could alter the moon's fragile exosphere. Even sunlight reflection from massive solar arrays might unintentionally warm nearby asteroids or space debris, creating unpredictable orbital shifts. The solutions may lie in biomimicry. Just as ecosystems on Earth recycle waste efficiently, future habitats could adopt closed-loop systems where every output becomes an input. Algae farms might scrub carbon dioxide while producing food and oxygen. 3D printers could repurpose plastic waste into spare parts, and rotating habitats themselves could become energy hubs, using their motion to generate supplemental power through dynamos, much like regenerative braking in electric cars. The ultimate test won't be whether we can build these habitats, but whether we can sustain them without repeating Earth's mistakes. A spinning city in space isn't just a technical marvel, it's a chance to prove humanity can thrive beyond our planet without exhausting its new frontier. The energy we harness must power more than machines. It must fuel a future where progress and preservation rotate in perfect balance. Building a spinning space habitat isn't just an engineering challenge, it's a materials science revolution in the making. Steel and aluminum, the backbone of modern construction, would buckle under the relentless stresses of rotation in the vacuum of space. Every material chosen must withstand not just the crushing centrifugal forces trying to tear the structure apart, but also extreme temperature swings, micrometeorite impacts, and relentless cosmic radiation. That's why researchers are turning to advanced composites like carbon fiber, reinforced polymers, materials light enough to launch economically yet strong enough to handle the equivalent of constant hurricane force winds. These aren't your everyday carbon fibers. They're woven with nanomaterials like boron nitride nanotubes, creating lattices where each strand is thousands of times stronger than steel at a fraction of the weight. But strength alone isn't enough. In the unforgiving environment of space, even microscopic cracks can spell disaster. That's where self-healing polymers come into play. Imagine a habitat wall that repairs its own punctures, much like human skin sealing a wound. Scientists are already testing materials embedded with microcapsules of liquid resin that burst upon impact, filling gaps and hardening under ultraviolet light. Other prototypes use shape memory alloys that remember their original form, bending back into place after collisions. These innovations aren't just theoretical, a Mars habitat project recently 3D printed a test dome using polymer composites laced with fungal spores that activate to seal cracks when exposed to moisture. The real game changer, though, might lie beyond Earth entirely. Transporting every bolt and beam from our planet's gravity well is prohibitively expensive, which is why lunar and asteroid mining could rewrite the rulebook. The Moon's regolith is rich in aluminum, titanium, and even glass-forming silicates. Companies like Redwire Space are developing orbital 3D printers that could process this raw material into habitat components, layer by layer, without ever touching Earth. Picture robotic landers scraping up lunar soil, solar furnaces melting it into printer feedstock, and autonomous assemblers constructing rotating rings on site. This approach doesn't just cut costs, it eliminates the risk of launching fragile megastructures through the atmosphere. Yet the most radical materials might not come from rocks at all. Mycelium, the root network of fungi, is being tested as a lightweight, radiation-resistant building block that could grow itself in space. Experiments aboard the ISS show fungal cultures thriving in microgravity, potentially forming living hulls that self-repair and even filter air. Meanwhile, researchers at the European Space Agency are exploring metallic foam's bubbly, lightweight structures that absorb impacts while providing excellent thermal insulation. The scale of these innovations will directly determine how ambitious our habitats can become. A 1-mile-wide Stanford torus requires materials orders of magnitude stronger than anything used in skyscrapers, while also being flexible enough to handle the subtle wobbles of rotation. Get the chemistry right, and we could see spinning cities hosting thousands. Get it wrong, and the consequences don't bear thinking about. That's why today's breakthroughs in labs and orbital trials aren't just academic. They're the invisible foundation of every artificial gravity dream, quietly ensuring that when humanity takes its first real steps toward living among the stars, our homes won't just spin, they'll endure. Who gets to make the rules when your neighborhood is a spinning cylinder orbiting Mars? The Outer Space Treaty of 1967, the closest thing we have to a galactic constitution, was written when space stations existed only in sketches. Its noble principles, like banning nuclear weapons in orbit and declaring celestial bodies the common heritage of mankind, now face real-world tests no one anticipated. Picture this: a corporation builds a rotating habitat near the Moon, mines lunar ice for profit, and claims exclusive rights. Does international law allow that? Can passengers aboard a commercial space station sue for faulty artificial gravity? The answers aren't just theoretical, they'll determine whether space becomes a new Wild West or a model of peaceful cooperation. Jurisdiction gets especially murky when habitats blur national boundaries. A station built by American company SpaceX, using Russian docking systems, orbiting over Brazilian skies with a multinational crew who handles crimes or contract disputes. Current maritime and aviation laws offer rough templates, but space introduces bizarre wrinkles. If a fistfight breaks out in a rotating habitat's Earth gravity section, then spills into a zero-G hub, does the location of the altercation change which nation's laws apply? Legal scholars are already drafting proposals, from flag state models where the habitat's country of registry governs everything, to hybrid systems with orbital zoning laws. Resource rights could spark even thornier conflicts. The Moon's south pole holds precious water ice in permanently shadowed craters vital for life support and rocket fuel. If one nation's base pumps that ice to supply its spinning habitats, does that deprive others? Existing treaties forbid territorial claims, but they're silent on extraction rights. Some suggest auctioning off orbital slots and mining zones like underwater cable routes, while others warn this could let wealthy nations monopolize space's riches. The solution might lie in adaptive systems, where legal frameworks evolve alongside technology, perhaps blockchain-tracked resource quotas or AI mediators to resolve disputes in real time. The stakes soar when considering military implications. A spinning habitat with strategic views over Earth could double as an observation post, raising surveillance concerns. While the Outer Space Treaty bans weapons of mass destruction in orbit, it doesn't address conventional arms. Could a nation station troops in an artificial gravity outpost under the guise of research? Some legal experts propose expanding the treaty to ban all orbital weaponry, while spacefaring nations resist limits on their defense options. The delicate dance between security and cooperation will require unprecedented transparency, maybe even shared monitoring systems built into future habitats. What makes these challenges so urgent is their first-mover advantage. Early precedents will shape behavior for decades, just like maritime laws established centuries ago still influence shipping today. Private companies are already lobbying for clear rules, knowing uncertainty stifles investment. Meanwhile, the United Nations Committee on the Peaceful Uses of Outer Space scrambles to modernize frameworks before conflicts arise. The ideal outcome: a system flexible enough to encourage innovation but robust enough to prevent exploitation, where artificial gravity habitats become laboratories not just for science, but for humanity's next great social experiment in shared governance beyond our planet. The gleaming towers of future space habitats may symbolize human ingenuity, but they also cast long ethical shadows we can't ignore. When the first spinning cities open their airlocks, deciding who steps inside won't just be about ticket prices or technical skills. It'll force us to confront fundamental questions about fairness in an off-world society. Consider the brutal math. Early habitats might house only a few thousand people while billions remain Earth-bound. Will access be determined by wealth, with the ultra-rich buying permanent residences while scientists and essential workers rotate on temporary contracts? Or should we implement lottery systems, giving ordinary citizens equal shots at becoming space pioneers? History offers sobering parallels, from colonial settlements favoring investors to climate shelters potentially prioritizing the privileged. Without deliberate safeguards, artificial gravity habitats risk becoming gilded cages orbiting above an overheating planet. Genetic adaptation introduces even thornier dilemmas. As researchers explore gene therapies to combat muscle atrophy or radiation sensitivity in space, we approach a crossroads. Should we modify humans to fit harsh environments, or reshape environments to preserve human biology unchanged? Some argue tweaking our DNA is no different from using vaccines or eyeglasses, just another tool for survival. But critics warn this could split humanity into subspecies, Earth-adapted and space-adapted. Imagine a child born in a Martian colony with reinforced bones and radiation-resistant cells who can never visit their ancestral home planet because Earth's gravity would crush them. These aren't hypotheticals. Studies show mice exposed to Mars-like gravity produce offspring with significantly different musculoskeletal development. The choices we make today about genetic thresholds could echo across generations. The ethics extend beyond human lives. Space habitats will require vast resources water mined from asteroids, metals extracted from lunar soil. While treaties declare celestial bodies the common heritage of mankind, enforcement remains shaky. A single corporation controlling a water-rich asteroid could hold life or death leverage over emerging space communities. Ecologists warn about repeating Earth's mistakes. Strip mining the moon's poles might disrupt fragile exospheres we don't yet understand. Perhaps the answer lies in circular economies where every molecule gets recycled, but achieving that demands unprecedented cooperation between rival nations and corporations. Perhaps the most profound question isn't technical but philosophical. What kind of society do we want to export to the stars? Rotating habitats could become laboratories for radical social experiments, testing everything from universal basic income in closed economies to AI-mediated governance. But they could also magnify Earth's inequalities, creating orbiting gated communities where the elite escape climate disasters. The difference lies in planning. Establishing ethical frameworks now before the first habitat spins up could ensure these structures uplift humanity rather than fracture it. After all, the gravity we create in space shouldn't just hold us to the floor, it should ground us in our shared humanity. Building the workforce for space habitats isn't just about filling job openings, it's about reinventing education from the ground up. Universities like MIT and Stanford have already launched specialized programs in space architecture, where students design rotating habitats using virtual reality simulations. But this is just the beginning. Future engineers won't just learn physics and math, they'll need hands-on experience with centrifugal force dynamics in orbital labs, or practice assembling mock habitats underwater to simulate zero-gravity construction. Imagine medical students training in spinning clinics to understand how artificial gravity affects drug absorption, or botanists studying plant growth in variable gravity greenhouses. The classroom of tomorrow might not have walls at all. It could be a prototype habitat module where every lesson unfolds in the environment students will eventually call their workplace. The demand for skilled labor will stretch far beyond engineers and astronauts. Picture a Martian colony's daily needs, chefs adapting recipes for low-gravity kitchens, psychologists trained to handle isolation in spinning habitats, even space plumbers troubleshooting water recycling systems in rotating environments. Technical schools are already pivoting to meet this need. The International Space University's hands-on programs, for example, teach students to repair life support systems while subjected to centrifugal forces mimicking Mars or Moon gravity. These niche skills will become as vital as coding or electrician training are today, creating career paths that don't yet exist on Earth. But education isn't just about technical skills, it's about acclimating minds to a radically different way of living. Future space residents will need to internalize concepts that defy Earth-bound intuition, like Coriolis effects altering how thrown objects curve in spinning habitats, or timekeeping synchronized to orbital cycles rather than sunsets. Schools might use immersive games where children navigate virtual rotating space stations, building spatial awareness for environments where down is a curved wall. Language itself could evolve. Terms like floor and ceiling might give way to inward and outward in habitats where every surface feels like the ground. The most profound shift, though, may be cultural. As space habitats become multicultural hubs, education will need to foster collaboration across borders and disciplines. A lunar base's success could hinge on how well a Russian life support specialist communicates with a Brazilian hydroponics expert, both trained under different educational systems but now relying on shared protocols. Universities are addressing this through programs like the European Space Agency's interdisciplinary courses, where teams solve habitat design challenges while navigating language barriers and technical jargon. The goal isn't just competence, it's creating a generation fluent in the unique blend of science, diplomacy, and adaptability that off-world living demands. This educational revolution won't stay confined to space. The same technologies developed for orbital training, like augmented reality simulating variable gravity or telerobotics labs for remote maintenance, will transform vocational schools and universities on Earth. A mechanic learning to repair centrifugal water purifiers for Mars could apply those skills to sustainable desalination plants in drought-stricken regions. The spin-off benefits might ultimately prove as valuable as the habitats themselves, turning humanity's leap into space into a rising tide that lifts all of education. Human creativity has always adapted to its environment, but spinning habitats will rewrite the rules of culture itself. Picture a ballet performed in variable gravity, dancers leaping impossibly high in the habitat's lower gravity center, then pirouetting gracefully as they descend toward the higher gravity outer rings. Or consider sculpture crafted from floating metals that solidify into forms impossible under Earth's constant pull. These aren't just new art forms, they're entirely new sensory languages born from living where gravity becomes a dial rather than a constant. Even something as simple as music transforms when sound waves behave differently in rotating atmospheres, inspiring composers to explore harmonies that would dissipate unnoticed on Earth. Sports will undergo radical reinvention. Traditional athletics rely on Earth's unchanging pull, but imagine basketball where players adjust shots mid-air to compensate for the Coriolis effect, or swimming in toroidal pools where laps become spirals. Teams might specialize in different habitat zones, players from the high-gravity outer rings built like powerlifters competing against lean, quick athletes from the lighter central areas. The very concept of up becomes negotiable in sports played on cylindrical courts where spectators surround the action from all angles. These games won't just entertain, they'll help space-born generations develop spatial awareness foreign to Earthlings, rewiring neural pathways through play. Social structures will bend under these new physical realities. Dating norms could shift when partners experience different gravity levels. Does someone from Mars' light gravity seem frail on Earth, or do Earth natives appear sluggish off-world? Family trees might branch strangely across gravity wells, with grandparents on Earth, parents on the Moon, and children in rotating orbit. Even body language changes in habitats where standing too quickly in low G zones becomes rude, like shouting in a library. These subtle behavioral adaptations will accumulate over generations, creating cultural divides as distinct as those between island nations on Earth. The most profound transformation may be linguistic. Today we say sunrise and sunset, but what phrases emerge when your home rotates to create artificial dawn? Perhaps spin up replaces morning, or axis tilt describes midday. Gestures could gain new meanings, pointing inward toward the habitat center versus outward to the walls might carry social significance lost on Earth. These linguistic shifts won't just describe new experiences, they'll shape how space dwellers perceive reality itself, much like how the Inuit language's multiple words for snow sharpen awareness of subtle winter variations. Identity itself becomes fluid in this environment. Children raised in rotating habitats may develop proprioception so finely tuned they can estimate gravity levels by how their hair falls. Their vestibular systems could adapt to handle multiple rotation speeds effortlessly, making them literally dizzy with culture shock when visiting Earth's monotonous gravity. Over centuries, these adaptations might crystallize into new human subspecies, not through deliberate genetic engineering, but through the slow pressure of environment on biology. A Mars-born poet might describe Earth's gravity as the old anchor, while an orbital historian refers to terrestrial life as the before-spin era. Yet amid these changes, constants will endure. The need for storytelling, the comfort of shared meals, the thrill of discovery, these human universals will persist even as their expressions evolve. The true test of our spacefaring civilization won't be whether we master artificial gravity, but whether we can maintain our humanity while spinning through the void. In habitats where every sunrise is engineered and every breeze carefully calibrated, culture becomes both our anchor and our sail, the weight that keeps us grounded and the force that propels us forward. The race to conquer space often feels like a high-stakes competition, with billionaires launching rival rockets and companies guarding proprietary technologies. Yet beneath the rivalry lies an inconvenient truth: no single entity can shoulder the colossal challenge of artificial gravity habitats alone. The International Space Station stands as proof of what's possible when competitors collaborate. 15 nations pooled resources to build this orbiting laboratory, sharing not just funding but decades of hard-won data on microgravity's effects. Now, as we pivot toward spinning habitats, that spirit of cooperation must evolve to match the scale of ambition. Private companies might battle for contracts and headlines, but behind closed doors, they're increasingly interdependent. SpaceX's Starship could launch modules for Blue Origin's orbital reef, while Sierra Space's inflatable habitats might integrate with Axiom's commercial extensions. This isn't altruism, it's pragmatism. The physics of artificial gravity don't care about corporate logos. A malfunctioning bearing in a rotating habitat could endanger lives regardless of whether it bears a NASA, a stamp, or a startup's insignia. That's why even fierce rivals are quietly standardizing docking mechanisms and emergency protocols, recognizing that shared safety frameworks benefit everyone. The real acceleration happens when competitors become collaborators. Take NASA Artemis Accords, a framework where signatories agree to peaceful exploration and transparent resource sharing. Over 30 countries have joined, including spacefaring nations and newcomers alike. These agreements create fertile ground for joint experiments like Japan testing centrifugal force modules on a U.S.-built lunar base, or European astronauts validating artificial gravity's effects on crops using Chinese-grown seeds. Such partnerships spread risk while multiplying insights, ensuring no single failure derails progress. Yet collaboration isn't just about avoiding duplication, it's about tackling problems too vast for any one team. Consider radiation shielding. A spinning habitat's outer hull must block cosmic rays without adding crippling weight. No company has cracked this alone, but together they're closer. Lockheed Martin contributes lightweight metamaterials, SpaceX shares data on hull stress during re-entry, and startups like Cosmic Shielding Corporation test innovative polymer blends. The result, a collective leap forward that outpaces any solo effort. The balance between competition and cooperation will define this era. Rivalry drives innovation. SpaceX's reusable rockets emerged from private sector hunger to slash costs, but unchecked competition wastes resources. Imagine 5 companies building separate lunar bases when one shared outpost could suffice. The solution lies in layered collaboration. Compete on breakthrough technologies, but cooperate on foundational infrastructure. Think of it like terrestrial highways. Private carmakers compete fiercely, yet all benefit from publicly maintained roads. The stakes couldn't be higher. Artificial gravity habitats represent more than engineering triumphs. They're the bridges to humanity's multi-planet future. Whether those bridges rise from cutthroat rivalry or shared vision will determine not just how quickly we build them, but whether they're sturdy enough to carry us all. The lesson from 60 years of spaceflight is clear. When we lift together, we rise farther. From the spinning wheel of 2001, a space odyssey, to the sleek rings of the expanse, science fiction has planted artificial gravity habitats in our collective imagination long before engineers drafted their first blueprints. These cinematic visions do more than entertain, they shape what we believe is possible. When Stanley Kubrick depicted a rotating space station with gravity-defying jogging tracks in 1968, it wasn't just groundbreaking special effects. it became a cultural touchstone that influenced generations of scientists. The reverse is also true. Misleading portrayals can breed skepticism. Films that handwave gravity as a solved problem with magical gravity plating leave audiences confused when real-world solutions involve painstaking physics and spinning structures. The gap between Hollywood fantasy and engineering reality matters because public enthusiasm fuels funding, and funding turns concepts into steel. Documentaries are bridging that gap by showcasing the gritty reality behind the dream. BBC's Tomorrow's World episodes from the 1970s introduced viewers to Gerard O'Neill's cylinder habitats with hand-drawn animations, making orbital cities feel tantalizingly close. Today, streaming platforms like CuriosityStream dive deeper, following engineers as they wrestle with gyroscopic wobbles and centrifugal force calculations in real time. These glimpses behind the curtain demystify the process, transforming abstract ideas into relatable challenges. When SpaceX live streams Starship tests, complete with fiery explosions and iterative redesigns, it doesn't just showcase failure, it teaches millions that progress is messy and that each setback inches us closer to viable solutions. Interactive experiences take this engagement further. Virtual reality simulations like Space Engine let users walk through meticulously modeled rotating habitats, feeling the disorientation of Coriolis effects when tossing a virtual ball across a spinning room. Museums are getting in on the Act 2. The Cosmosphere in Kansas features a centrifuge ride that mimics partial gravity, while Tokyo's Murikan Museum uses augmented reality to overlay futuristic habitat designs onto its exhibits. These hands-on encounters do what articles and lectures can't. They make artificial gravity tangible. A child who feels Mars-level gravity in a spinning simulator doesn't just learn about centrifugal force, they internalize it, sparking questions that might lead to future breakthroughs. Yet media's role isn't just education, it's emotional persuasion. When National Geographic visualizes a day in the life of a Martian colonist, showing families tending hydroponic gardens under artificial sunlight in a rotating habitat, it doesn't just explain the science, it sells the lifestyle. This narrative shift from survival to thriving resonates deeply. Climate change documentaries like The Year Earth Changed have primed audiences to see space habitats not as escapes from Earth, but as extensions of our commitment to preservation. The messaging matters. Frame habitats as lifeboats for the elite, and public support crumbles. Position them as laboratories for sustainable living that could benefit Earth, and curiosity flourishes. The challenge now is balancing wonder with honesty. SpaceX's glossy renders of Mars bases inspire, but they rarely show the decades of trial and error required to build them. Meanwhile, dystopian sci-fi like The Martian overemphasizes isolation and danger, overshadowing the collaborative joy of solving problems together. The sweet spot lies in stories that acknowledge the struggle while celebrating the human ingenuity behind each milestone. When Apollo 13 showed astronauts jury-rigging solutions in crisis, it didn't diminish the space program, it made the triumph sweeter. Artificial gravity habitats need their own Apollo 13 moments, narratives that honor the grind while keeping the stars within reach. Ultimately, public perception will determine whether these projects ascend beyond blueprints. Every viral tweet comparing a spinning habitat to a cosmic carousel, every classroom debate about the ethics of off-world settlements, every crowd-funded experiment testing centrifuge-grown plants, they all weave a cultural narrative that either propels the mission forward or leaves it grounded. The media doesn't just reflect our hopes for space, it shapes the gravitational pull of possibility itself, drawing us steadily toward a future where spinning homes in the void feel less like science fiction and more like tomorrow's front-page news. Fusion propulsion could revolutionize how we reach and sustain artificial gravity habitats, not just as a faster way to travel, but as a continuous power source for spinning megastructures. Unlike traditional rockets guzzling finite fuel, fusion reactors harness the same energy that powers stars, potentially generating thrust for years from mere grams of hydrogen. Picture a Mars-bound craft where the reactor doesn't just propel the ship it powers onboard centrifuges, creating gravity during the voyage so astronauts arrive stronger than they left. Startups like Helion Energy are already testing compact fusion prototypes that could one day anchor orbital habitats, their steady energy output eliminating the need for sprawling solar arrays in deep space. The implications are staggering. Habitats might spin indefinitely without draining batteries, turning what was once a power-hungry liability into a self-sustaining system. Yet propulsion is just one piece of the puzzle. Managing a rotating habitat's delicate balance requires real-time precision beyond human reflexes. Enter artificial intelligence. AI-driven systems could monitor thousands of sensors, adjusting rotation speeds to compensate for shifting weight distributions as residents move or cargo is unloaded. Imagine smart gyroscopes that predict wobbles before they happen, or neural networks optimizing energy use by syncing habitat rotation with solar flare warnings to reduce radiation exposure. These aren't distant fantasies. NASA Artemis missions are already testing AI assistants that control life support systems, laying groundwork for more complex gravity management. The true breakthrough lies in merging these technologies, fusion providing clean energy, while AI ensures every watt is used to keep habitats stable and safe. Construction methods are also leaping forward. Why risk human lives assembling giant rotating structures in orbit when autonomous robots can do it first? Companies like GitHi are developing orbital construction drones that weld, bolt, and inspect components with millimeter accuracy. These machines could prep habitats years ahead of human arrival, linking modular sections into sprawling rings, all while enduring the punishing conditions of space without fatigue. Japan's space agency recently demonstrated a tether-based assembly bot that can maneuver massive payloads into place using centrifugal force itself as a tool. The robots might even harvest raw materials on-site, melting lunar regolith into structural beams or 3D printing frictionless bearings from asteroid metals. This shift changes everything. Instead of launching fragile prefab habitats from Earth, we could send compact robotic crews that build disaster-resistant megastructures in situ. The timeline compression is equally transformative. Traditional space projects drag across decades, but combining these technologies could slash development cycles. Fusion-powered transports might cut Mars travel time from months to weeks, while AI and robots accelerate construction from years to months. Private firms like Vast Space are already betting on this acceleration, proposing habitable modules that go from blueprint to orbit in under 5 years, a pace unthinkable during the Apollo era. The ripple effects extend beyond speed. Quicker builds mean earlier revenue from research leases or tourism, creating financial incentives that fuel further innovation. What ties these breakthroughs together is risk reduction. Every autonomous builder eliminates a dangerous spacewalk. Every AI monitor prevents a destabilizing imbalance. Every fusion reactor dodges a catastrophic power failure. The result, artificial gravity transitions from a high-stakes experiment to a reliable utility, as commonplace in future space colonies as electricity is today. The technologies on the horizon don't just make spinning habitats possible, they make them practical, turning the dream of thriving in space into an inevitability. The 2040s might sound like science fiction, but that's when experts predict the first artificial gravity habitats could swing into operation, less than 2 decades from today. The timeline isn't just guesswork, it's backed by concrete milestones already in motion. Lunar prototypes could arrive even sooner, with NASA Artemis program planning a sustained human presence on the Moon by the 2030s. These early bases won't be spinning megacities, they'll likely feature compact centrifuges, like the one proposed by Lockheed Martin, where astronauts spend a few hours daily to counteract muscle loss. These modules will serve as testing grounds, refining the balance between rotation speed and human comfort before scaling up. Mars presents a trickier timeline. While SpaceX aims for crewed missions by the 2030s, full-scale rotating habitats there might not emerge until the 2040s or beyond. The delay isn't just about distance, it's about infrastructure. Building a spinning structure on Mars requires either launching prefabricated sections from Earth, a costly endeavor, or developing local manufacturing using Martian resources. Both approaches hinge on advancements in robotics and 3D printing. Companies like Icon, already 3D printing homes on Earth, are working with NASA to adapt their tech for lunar and Martian regolith. Once these technologies mature, Mars could see its first gravity-augmented habitats, perhaps hybrid designs where residential rings rotate around static industrial zones. Funding remains the wild card. The International Space Station cost over $150 billion across 30 years, but private investment is changing the calculus. Analysts at Morgan Stanley estimate the space economy could top $1 trillion by 2040, with habitats as a key driver. The quicker companies like Axiom Space and Orbital Assembly monetize early stations through tourism, research leases, or manufacturing, the faster capital flows into larger projects. Government budgets will still play a role, especially for high-risk components like radiation shielding, but the era of solely taxpayer-funded megaprojects is ending. Global cooperation could accelerate progress or bottleneck it. The Artemis Accords, signed by over 30 nations, suggest a collaborative framework for lunar development, yet tensions over resource rights loom. China's plans for a lunar research station and Russia's nuclear space tug program hint at parallel efforts outside Western alliances. History shows that competition spurs innovation, but duplication wastes resources. The ideal scenario, a mix of healthy rivalry in design and shared standards for critical systems like docking ports and emergency protocols. The most surprising variable isn't tech or money, it's public will. The Apollo program captured imaginations because people could watch grainy footage of boots on lunar soil. For habitats to galvanize similar support, they'll need visible wins, live streams of astronauts jogging in a rotating module, or a child's drawing of their future home in a spinning Martian city. When these images enter the cultural bloodstream, political and financial priorities shift. The 2040s aren't a distant future. They're the horizon we're already sprinting toward, and every blueprint, test spin, and lunar prototype brings it closer. The countdown hasn't just started, the clock is ticking louder by the day. Training for life in artificial gravity won't just involve strapping astronauts into centrifuges, it'll demand a complete rewiring of how we prepare for space. Earth-based simulations are already giving us a glimpse of what that future looks like. At facilities like NASA Ames Research Center, volunteers lie sideways on rotating beds for weeks, their bodies tilted so that centrifugal force mimics gravity's pull. These studies reveal surprising quirks. Some test subjects adapt within days, while others struggle with nausea or spatial disorientation long after the spinning stops. The findings are shaping a new era of astronaut training, where resilience to rotation becomes as critical as mastering zero-G maneuvers. but physical adaptation is only half the battle. Future spacefarers will need fitness regimens tailored to hybrid environments where workouts in Earth's full gravity prepare muscles for habitats that might simulate Mars' lighter pull or lunar conditions. Picture a gym where treadmills tilt at varying angles to replicate different centrifugal forces, or resistance machines that account for Coriolis effects unique to spinning structures. Nutritionists are also rethinking meal plans, since digestion and metabolism shift under artificial gravity. Studies on the International Space Station show that nutrient absorption decreases in microgravity, while rotating habitats require vitamin-enriched foods or timed supplements to compensate. The answers could determine whether settlers maintain bone density or succumb to subtle deficiencies over years. Psychological preparation may prove even more vital. Floating in microgravity feels alien at first, but at least it's consistent. In a spinning habitat, simply walking from a high-gravity outer ring to a lighter central hub could trigger sensory whiplash. Virtual reality programs are being developed to acclimate crews to these transitions, immersing them in simulations where corridors curve unnaturally and dropped objects don't fall straight down. Behavioral scientists are even studying sailors and submariners, groups accustomed to confined, motion-heavy environments, to draft guidelines for maintaining mental health amid constant rotation. The most radical training might happen far earlier than we expect. Schools in spacefaring nations could incorporate centrifugal exposure into their curricula, much like scuba certification courses today. Teenagers might earn gravity adaptation badges by completing progressively longer stints in rotating simulators, building tolerance over years rather than weeks. This gradual approach could be key for children whose developing bodies and brains may adapt more readily than adults, potentially raising a generation for whom adjusting to off-world gravity feels as natural as learning to ride a bike. Ultimately, the goal isn't just survival, but seamless integration. The smoothest artificial gravity will be the kind we forget is even there, where a researcher can focus on their experiment without noticing the habitat's spin, or a child can chase a ball without calculating its curved trajectory. Achieving that invisibility requires starting preparations long before launch day, blending physiology, psychology, and cutting-edge tech into a training regimen as revolutionary as the habitats themselves. The future of space living isn't just about building better hardware, it's about crafting humans who can thrive within it. The race to build artificial gravity habitats isn't just about engineering marvels, it's about rewriting the human story. For the first time in history, we're not just visiting space, we're learning how to truly live there, to raise families under manufactured skies, and to thrive in environments where every sunrise is carefully calculated. This isn't merely a technical challenge, it's a cultural, biological, and philosophical revolution wrapped in spinning metal and glass. The implications stretch far beyond astronauts. Imagine artists painting in lunar studios where brushes glide differently, or children playing sports in rotating domes where the Coriolis effect bends every throw into a curveball. These habitats won't just preserve our bodies in space, they'll redefine what it means to be human when home could be a cylinder orbiting Jupiter or a spinning outpost on Pluto's icy plains. What makes this moment extraordinary is the convergence of necessity and opportunity. Earth's growing fragility, from climate crises to resource depletion, pushes us toward the stars, while breakthroughs in robotics, fusion energy, and materials science pull us upward with newfound feasibility. The International Space Station taught us how fragile humans are in microgravity. Now, artificial gravity habitats offer the missing piece, a way to stay healthy while reaching farther. Mars missions once seemed impossible due to the toll of zero gravity. Now, spinning transit modules could make interplanetary travel as routine as intercontinental flights. The shift is profound. We're no longer trying to survive space's harshness, but to domesticate it. Yet the true measure of success won't be technological, it'll be emotional. When a baby takes their first steps in a habitat's curved park, or when grandparents watch Earth rise from their rotating porch, that's when the abstract becomes real. This isn't just about escaping a troubled planet. It's about expanding the human experience in ways we're only beginning to imagine. The cultures that emerge in these habitats, their music, their slang, their very dreams, will diverge from Earth's as dramatically as island nations once did from continents. The question isn't whether we'll build these spinning havens, but how quickly we'll embrace their potential. Will they become exclusive enclaves for the wealthy or springboards for all of humanity? The answer depends on choices we're making right now about funding, about ethics, about who gets to call the stars home. One thing's certain, the era of clinging to Earth's gravity is ending. The future belongs to those bold enough to spin their own. So as rockets rise and prototypes whirl in testing chambers, remember, you're witnessing more than machines. You're seeing the first drafts of a new chapter in human history, one where gravity is no longer a chain but a tool. Where will we take it next? The trajectory is up to us. Hit subscribe and let's navigate this cosmic turning point together, because the greatest adventures don't just happen in space. They happen when we decide to reach for them.